All right, so in this video, we're going to talk about the law of large numbers. So the idea that large numbers of events may show some pattern even while individual events are unpredictable is called the law of large numbers. It's also called the law of large averages, but we're typically going to call it the law of large numbers in the course. So it applies to a process for which the probability of an event A is P of A, and the results of repeated trials do not depend on results of earlier trials. So they're going to be independent results. The law of large numbers states that if the process is repeated through many trials, the proportion of the trials in which event A occurs will be close to that probability of A. The large number of trials, or the larger number of trials, the closer the probability should be to what we expect. So if we think about flipping a coin, right? Let's just go into a little bit of clarification. If I'm looking at flipping a coin, I expect the probability of getting heads to be 1 out of 2. But if I only flip 4 coins, and let's see if this will work in my favor. Okay, I'm flipping 4 coins here. Oh, and in flipping 4 coins, I actually got 4 tails. So I didn't get any heads. If I had flipped 1 head, which was what I was hoping, I got 1 head out of 4 flips. But what this is saying is that the more times I flip, so that would be like 1 out of 4, right? We had a 0 out of 4, which is a possibility. But the more times I flip a coin, and I have some more, so these were all tails. Let's keep going. But I didn't even really flip, right? It just flew out of my hand. Okay, this one flipped up heads. We're getting a lot of tails today. There's another head. That's another tail. Lots of tails. I usually don't get this many tails. All right. So in this case, I don't even know how many we flipped. We've got 2, 4, 6, 8. All right. So here we've got 8 tails, and we've gotten 4 heads. So the more that we continue to flip, the more it's going to balance out. So they're saying that the larger numbers that you flip of these, the closer you'll get to having 50%. So I would expect if I flipped 12, I would get 6 heads and 6 tails. But that's not always going to be the case. So if we were in the classroom, I would give everybody a coin, a penny, and we would flip. You'd flip 10 times, and then we'd write down the numbers of how many heads and how many tails. Because I don't want to flip the coin, let's say, if there were 10 students in the class, I don't want to flip it 100 times. But if everybody in the class flipped it 10 times, and we add up all the heads and all the tails, 100 flipped coins is more than, in this case we have 12, but even if we had 10. So therefore, you're going to get closer to that 50-50 because we know the probability of getting a head is 1 out of 2. But that doesn't mean when you just flip it a couple of times, you're going to get 1 out of 2. Or if you flip it, 4 times, that you're going to get 2 heads and 2 tails. That's just the probability of it happening. But the law of large numbers says the more times you flip it, you'll get closer and closer to that expected value of 1 out of 2. So here's our expected value. So it's the expected value of a variable is the weighted average, we've talked about that before, of all its possible values. Because it's an average, the expected value is likely to be close to the actual value, only when there are a large number of events. If it's a small number, it may not get there. So that's where the law of large numbers is going to come into play. Now to calculate the expected value, you're going to take, if we're considering 2 events, you'll take the expected value is going to be the value of event 1 times its probability of it happening plus the value of the event 2 times its probability of occurring. So this formula can also be extended to a number of events. So we could, if we had a third event, we'd add the value of event 3 times the probability of event 3. Now there's another thing that's called the gambler's fallacy. So it's the mistaken belief that a streak of bad luck makes a person due for a streak of good luck, or that a streak of good luck will continue. So one reason people succumb to the gambler's fallacy is the misunderstanding of the law of large numbers. Another common misunderstanding that contributes to the gambler's fallacy involves the expectation about streaks. So a little bit more about the gambler's fallacy means that this is where it gets its name kind of from gambling, right? So when a gambler goes and they're losing all kinds of money, they feel that they're due for a win. If I just keep playing, I'm going to win, I'm going to win, I'm going to win. And it'll turn it around. So they're expecting that they are due for a streak of good luck, and if they just keep gambling, they will win their money. And so that's where it's a fallacy, because that doesn't mean that. It's not that you're due for anything. It just there's a chance of winning or losing, right? And you're either going to win or not. So let's consider a simple game involving a coin toss. If you win $1 if the coin lands on heads, and you lose $1 if it lands on tails. So heads and tails. I guess the older coins are better for this because they don't have as much glare maybe. There we go. So win $1, lose $1. So suppose you toss the coin 100 times and get 45 heads and 55 tails. Well, that's close. That's getting closer to our 1 out of 2, our 50% average, right? But you're going to actually be $10 in the hole because you have 10 more tails than you have of heads. So you gained $45, but you've lost $55. So you owe $10. You've lost $10. Are you due for a better streak of luck? Well, no. Because the law of large numbers tells us that eventually what will happen is we'll probably break even, but we're not necessarily going to win. Okay? We'll break even that if we keep it up, you'll get closer and closer to 50 and 50, but typically you're not going to walk away with money. Now, sometimes you do win, and then sometimes you lose. But if we're looking at the probabilities of things, the law of large numbers, we're going to expect it's going to balance out. But the gambler's fallacy is saying that, well, if I just keep going, I'm going to win. Well, you could end up losing for a while still. And you might run out of money before you win it back. All right. Suppose, example 1, the Insure-All company sells a special type of insurance that pays you $100,000 in the event that you quit your job because of serious illness. Based on data from the past claims, the relative frequency probability that a policyholder will make a claim for loss of job is 1 in 500. Should the insurance company expect to earn a profit if it sells the policies for $250 each? All right. So if Insure-All sells only a few policies, we're going to talk about what happens. So if they only sell a few policies, let's say we sell 100 policies. We're going to talk a little bit of some numbers to understand this. So this is 6.3, example 1. So this is an if. If they sell 100 policies, for $250 a piece. Well, 100 policies times $250 will get them $25,000. Okay? Now, if none of the 100 policy holders file a claim, the company would make a tidy profit of $25 or $25,000, right? However, if they have to pay $100,000 for any of those claims, even to one policyholder, they're going to face a huge loss. So if they had to pay $100,000 to even one of those people, just one of them, 99 didn't, but one person does, they didn't bring in enough money to cover that. They're $75,000 short to pay that $100,000, right? They'll be short $75,000. Now, if they go with the law of large numbers, let's say it tells us that the proportion of policies for which the claims will have to be paid should be close to that 1 in 500. That's what it said in our deal. They make a claim for a loss of a job is 1 in 500. So they sold a million, let's see, that they sold 1 million policies. We're just going to go with a bigger number. That's what we're doing here. So if we say that they have 1 million policies, and the chance of paying out one of those claims, 1 out of 500, will get us, that's basically $1 million divided by 500, or put it in your calculator, is 2,000 claims. Out of 1 million, they're going to get 2,000 claims for that money because they bought the insurance. Now, if we pay out 2,000 times 100,000 per claim, that's going to be $200 million. That's how much they're going to pay out, right? Now, the thing is that with this money, how much did they bring in? Well, if they sold 1 million policies times $250, this will get us $250 million. So this is how much they brought in, and this is how much they paid out. So the question is, should they expect to make a profit? Well, if I take 250 million minus the 200 million that they paid out, they will be left with 50 million. That's how much their profit would be. But that's why they have to sell so many policies. Now, it's 1 in 500. It could give or take, and sometimes things happen where they get a lot more going on. When all of a sudden everybody lost their job kind of thing. So due to a severe illness is what the thing was on this one. But you could have something come through where a lot of people got sick, and so maybe they'll lose more in a year or not. But on a typical one, they're going to make about $50 million because they brought in $250 million, and they're going to pay out $200 million. All right, so should they make a profit? Yes, they should. All right, let's go look at example 2. All right, for example 2, does it make sense? For the daily lottery in which you pick 3 numbers, is it better to select 539 than the numbers 1, 2, 3 because 539 is more random? All right, so here's the deal. Each number has its equal chance of being drawn, right? 1 through 9. It doesn't matter which ones you're choosing. I mean, it does like when it gets drawn, but when you're randomly picking them, they're all random. 539 is not more random than 1, 2, 3. It's just the order of which you pick them. It appears more random because 1, 2, 3 we think of being in an order, but it has nothing to do with the chances of winning. So it does not make sense. And all sets of the 3 numbers have the same chance of winning. Okay? Now, doesn't mean they're all going to win. They just have the same, not change, sorry. That should be chance. The same chance of winning. That's what we're talking about. With probability, it's the chance of something occurring. It's the chance of something happening. Doesn't mean it's going to happen exactly that way. It just means it's the chance for it to occur. Make sure you do your homework.